Welcome to the last section we're going to do in Chapter 3, 3.5 Part 2, Exponential Growth and Decay and Modeling Data. This is the last section of Chapter 3. So, our essential question is, in what elements of life might we see exponential decay? So there's Newton's law of cooling. The temperature T of a heated object at time t is given by T equals C plus the original T minus C times e to the kt, where C is a constant temperature of surrounding medium, T sub O is the initial temperature of the heated object, and K is the negative constant that's associated with the cooling of the object. So I would write this part down. So an object is heated to 100 degrees. So that means my 100 goes in TO. This is my initial temperature. It is left to cool in a room that has a temperature of 30 degrees Celsius. So my constant temperature goes where my C is. That's your 30. After 5 minutes, which is my time, the temperature of the object is 80 degrees. Use Newton's law of cooling to find the model for the temperature of the object T after T minutes. So in this case, we're going to solve for K first. So we need to solve for K in order to be able to solve for anything else. So this is 50 equals, nope. I'm going to rewrite that. So I subtracted 30 from both sides, so I have 50 equals 100 minus 30 is 70 e 5k. Divide both sides by our 70 and then simplify it. So we have 5/7 equals e 5 to the k. Now we're going to take our ln. So the equation in this situation is going to be T equals 30 plus 70e negative 0.0673 T. So when we're looking for the time, this is what we would have. So let's solve a problem where we have the new equation, but we're looking for a different piece now. So an object is heated to 100 degrees Celsius. It's left to cool in a room that has a temperature of 30 degrees. That's what we already have. After 5 minutes, the temperature of the object is 80 degrees. What is the temperature of the object after 20 minutes? So this means instead of T, we're going to have 20. So we have T equals 30 plus 70 E minus negative . If you plug that into a calculator, you would get, well, let's actually plug it in. So we have our calculator, and we're going to plug in our equation. So we have 30 plus 70 e, and we have negative 0.0673. Multiply that by 20. So you get 48.21955, etc. So you have about 48. So the temperature is about 48 degrees after 20 minutes. Now this part wants to know, so when will the temperature of the object be 35 degrees Celsius? So now we're going to look for T. So you have 35 equals 30 plus 70 E negative 0.0673 T. I'm going to divide both sides by 70, and then we're just going to leave it at that. We're not going to simplify it. If you would like to simplify your 5 over 70, you are more than welcome to. I'm not going to. So we're going to take the ln, natural log of both sides. You have ln 5 over 70 equals, divide both sides. So let's plug this one into our calculator as well. So I'm going to put it in parentheses, but we have ln 5 divided by 70. And that whole thing divided by negative 0.0673. You get 39.2133, etc. So this means your answer is about 39. So after 39 minutes, your temperature will be 35 degrees Celsius. So make sure when you do this, you're solving for the correct thing, and when you answer it, you know, okay, so what was it asking? When will the temperature of the object be 35? So I solved for 39, so in time, when is 39 minutes? So expressing y equals a times b to the x in base e. So if you have y equals a times b to the x, that's equivalent to y equals a e to the ln b times x. Write down that equivalency for now. So we're going to rewrite y equals 4 times 7.8 to the x in terms of base e. So we're going to express this in natural log and then round to 3 decimal places. So this really equals So make sure you solve this part. So you have y equals 4e 2.054x. And that's all you had to do for this one. So you're just expressing it with e instead. Make sure you complete the questions below and complete your homework, and I will see you in live class.